This video is part 3 of a lecture on section 5.4 from Math 311, a course on linear algebra at Western Illinois University. Okay, so we proved some theorems, including the spectral theorem, which shows that a matrix, a real square matrix, is orthogonally diagonalizable if and only if it's symmetric. So if a matrix is not symmetrical, we don't even have to waste our time trying to orthogonally diagonalize it. Just want to give another example of this before we go on. Let's look at a 3 by 3 matrix. We can see by inspection that this is symmetric. It's symmetric with respect to the well, it's equal to its own transpose. We can also see it's symmetric with respect to the diagonal. And so let's go and find the eigenvalues. The determinant of A minus lambda I is the determinant of 2 minus lambda 3, 0, 2 minus lambda 4, and 0, 4, 2 minus lambda. Okay, this is going to be a little slightly harder determinant to take, but not too much. We can expand along the top row, and we'll get 2 minus lambda times the determinant of 2 minus lambda 4, 4, 2 minus lambda, minus 3 times the determinant of 3, 4, 1, 0, 2 minus lambda. Okay, so this will be 2 minus lambda times 2 minus lambda squared minus 16 minus 3 times 3, 2 minus lambda minus 0. And this will be, you'll still see that 2 minus lambda is going to be a factor of both of these, so that will help us out immensely. So we can write 2 minus lambda going to be this 2 minus lambda squared minus 16, and then we have minus 3. So that will be minus 9. But this is 2 minus lambda times lambda squared minus 4 lambda plus 4 minus 16 minus 9. And this will be 2 minus lambda, so lambda squared minus 4 lambda minus 21. And fortunately for us, that factors as lambda minus 7, lambda plus 3. Okay, we set that equal to 0. And so we can see our eigenvalues will be lambda equals 2, 7, and minus 3. All right. If we plug in lambda equals 2 here, this matrix becomes 0, 3, 0, 3, 0, 4, and 0, 4, 0, where you say x, y, z, you want that to be 0. You can see easily that with the first one tells us that 3y equals 0, so y has to be 0. And then the second line says that 3x plus 4z equals 0. Okay, so for this we can just take, there are lots of eigenvectors, but you can figure out that 4, 0, 3, 4, 0, negative 3 is going to be an eigenvector for this. For lambda equals 7, we get 2 minus 7, that's negative 5, 3, 0, 3, negative 5, 4, and 0, 4, negative 5. Okay, and from here, once again, if you set x, y, z equals 0, you get that 5x, you get negative 5x plus 3, 4 plus 3y equals 0. So you get 5x has to equal 3y. And from the last one, we get 4y plus 5z has to equal 0. And the last one you can check is just sort of dependent on the other two. But you'll see that when everything is said and done, I believe 3, 5, 4 will work. Yeah, 3, 5, 4. And then I'm going to let you check that when lambda equals -3, our matrix is 5, 3, 0, 3, 5, 4, and 0, 4, 5 equals 0. So that I'll let you check that the other one is going to be -5, 4. I'm sorry, -3, 5, -4. Okay, hopefully you can check that that works out okay. Okay, so these are our three eigenvectors. You can check that they're orthogonal to each other, but we want to normalize this. Let's normalize this to get our matrix. So this is, we can see that the length of this is going to be 16 plus 9, which is 25. So we can just replace this with 4. Square root of 25 is 5, of course, so this will be 4/5, 0, -3/5. This is going to be, the length of this is 9 plus 25 plus 16. So this is, so if you add those together, I think it's 50. So we'll get 3 over square root of 50, 5 over square root of 50, and 4 over square root of 50. And then similarly, this will be -3 over square root of 50, 5 over square root of 50, -4 over square root of 50. So we can take these to be the three columns of our matrix. So this is Q. We can just take Q to be 4/5, 0, -3/5, 3 over square root of 50, 5 over square root of 50, 4 over square root of 50, and -3 over square root of 50, 5 over square root of 50, and -4 over square root of 50. That's our orthogonal matrix, and then our diagonal matrix is just going to be the eigenvalue that corresponds to these corresponding traits. So it would be 2, 7, -3, and zeros everywhere else. Okay. So that will under this we get that Q transpose AQ is equal to D. Okay. Hopefully that works. All right, this one, of course, I did pick the nastiest example in the book. This is actually problem number 6, in case you were wondering from this section. To wrap up, I want to talk about spectral decomposition. If we go back to our first example, where we took this matrix A 3, 1, 1, 3, and we wrote this way. It turns out that we can actually write this out in a slightly this matrix in a slightly different form. We can write this as 4 times something plus 2 times something, and this will turn out to be 4 times the dot product of the first column with itself. And I'm sorry, I don't mean dot product. This is the matrix product of the first column times its transpose. This is actually going to be a 2 by 2 matrix, because this is 2 by 1 and this is 1 by 2. So it's going to be a 2 by 2 matrix. and this will turn out, and 2, this is 2, we have to take the second column times its transpose. Okay, and if we do this, we get that, we see that this is 4 times 1/2, 1/2, 1/2, 1/2, and this is 2 times 1/2, negative 1/2, negative 1/2, 1/2. And in fact, this when you multiply this all out, this in fact is 3, 1, 1, 3. And this is called the spectral decomposition of the symmetric matrix A. And the way that goes, the general formula is that if Q can be written as Q1, Qn, and D is lambda 1 through lambda n, then A can be written as Q1 times Q1 transpose, or I'm sorry, A will be lambda 1 times Q1 transpose plus lambda 2 Q2 transpose all the way to lambda n Qn transpose. Okay. So that's the spectral decomposition of A. And you might need this later on. Okay, you maybe not in this course, but later on. But you should be aware of that. And one nice little thing about this is you can use this to come up with, you can, if you don't know what A is, but if you know what the eigenvalues are and some of the eigenvectors, you can sort of reconstruct an A from this formula. And that's what we do in this last example. Let's suppose we wanted to find a real symmetric 2x2 matrix with the following eigenvalues and eigenvectors. Well, here again, the eigenvectors can be are 1, 1 and 1, negative 1. And we can replace these with 1 over square root 2, 1 over square root 2, and 1 over square root 2, negative 1 over square root 2. And then we can just take A to be negative 2 times Q1 transpose, and Q2 and 4 times Q2 transpose. So let A be negative 2 times Q1 transpose plus 4 times Q2 transpose. And in fact, this will be negative 2 times, we just found out that this is just 1/2, 1/2, 1/2, 1/2. And this is plus 4 times 1/2, negative 1/2, 1/2, negative 1/2. When you do the calculations, this is going to be negative 1 plus 2, so that'll be 1. This will be negative 1 minus 2, so that'll be negative 3, and then this will be negative 3, and this will be 1. If I did that right, or did I screw this up again? Let's see. Oh, what did I do? Oh, yeah, yes, I did screw that up again. This should be this. Okay. Yeah. So this would be negative 3, 1. Okay. So that would be that case. So you can check that this works or not. So that's a nice little application of the spectral theorem, and this is spectral decomposition, which you might or may not be impressed with. So, so it's a long lecture, long series of lectures. The main thing is you want to the actual computation in most of the problems I'll give you from the textbooks is really just doing the same thing you did with diagonalization. You're just normalizing the eigenvectors before you go ahead and find your matrix. So, thank you, and we'll see you next time.